So first we'll have Martha White give a talk, and then we'll have the discussion period. So Martha, thank you for talking today, and looking forward to hearing your talk. Please take it away.
Great, thanks, Mark. So like Mark said, I'm Martha White. I'm at the University of Alberta, and today I'm going to talk a little bit about how we're going to generalize this objective called the projected Bellman error. It's an objective near and dear to my heart, but mostly been used for the linear setting, and how we're going to do that in a nice sound way for the nonlinear setting. And of course, this is a workshop about deep RL, so we want to ask how can we take some of our really nice theory and formalisms from the linear function approximation setting and bring it as much as possible to the nonlinear function approximation setting. All right, so this is 20 minutes is very short. I actually have lots of things that I want to tell you because there's been some really nice developments in this area. And actually lots of cool stuff from Bo Dai and Li Hong actually that I'm going to be giving call outs to in this talk. So I'm going to try to go at a reasonably fast pace, knowing that we're going to have 10 minutes at the end, where we can always go back and ask more questions and look at specific slides. Okay, so what's my goal? My goal here is to estimate values. I'm going to talk mostly about the prediction setting. So we're going to be estimating V pi with some approximation V, but actually a lot of this stuff extends also to the control setting. But let's make it more straightforward and talk first about prediction. So my goal is to estimate this V pi. If we could, we'd minimize this value error objective, but we can't actually directly optimize this objective. And here, usually in this objective, we're also going to have this weighting over states where the weighting is given by some D that tells me how I want to trade off my function approximation resources. Okay, so we can't directly optimize this objective. So a lot of questions that arise for the value estimation problem is, well, then what objective should we use? And so there's a long history here trying to understand what kind of objectives should we use for value estimation. And in fact, even sound off-policy value estimation was an open problem for quite some time. You know, everyone used TD. TD is a beautiful algorithm. QLearning is a beautiful algorithm. They have stood the test of time, but yet we know they have soundness problems. So there was a lot of progress made though once there was an introduction of an objective called the mean squared projected Bellman error. So I'm going to be calling that PBE with a line above it for mean. Okay, and then there's this just explosion of many different gradient algorithms that we could say things about how sound they were for value estimation, and it is beautiful. And still we sort of have a few open questions. So one thing is that this projected Bellman error is largely defined for the linear setting. Most of the algorithms are derived for the linear setting. And there is actually one nice work about the nonlinear projected Bellman error from Chaba and Hamid. And there they sort of do this natural thing where they use like a local linear approximation, but the resulting algorithm ends up being a little more complex, where you take gradients through gradients, you get Hessian vector products. And those actually quite a nice algorithm. We've tried it. It can perform well in practice. It hasn't had a lot of uptake, I think, because of this complexity. And on the flip side, so now we are asking how are we going to bring some of this stuff to the nonlinear case. The Bellman error has always been applicable to both. We could use it for the nonlinear or linear setting. In the projected Bellman operator, where the projected Bellman operator uses a projection that's harder to compute for the nonlinear setting, which is one of the reasons we've been using it so much in the linear setting. But the Bellman error has its own problems. So one thing for a very long time is that it was considered difficult to optimize because of the double sampling problem. And so I think that was one of the reasons it was sort of put to the side and the projected Bellman error explored more. And then more recently, also Rich in his book has shown that it has some identifiability issues as well, which is, you know, red here for a reason as well. That's problematic. So we're sort of in this case where we didn't know how to use the Bellman error. The projected Bellman error was a bit harder to extend in the nonlinear setting. And now there's actually recently been some really nice developments reformulating the Bellman error with the conjugate form from Bo Dai and Li Hong and others that I think is very promising. And that's what this talk is going to build on, those nice positive developments. Okay, so what I'd like to try to motivate in this is that we want to figure out how to extend the linear projected Bellman error to the nonlinear case. And particularly because we care about nonlinear function approximation, and we want to ask what is the right objective. So it's a sort of a big question. It's always a strong thing to say what is the best thing or the right thing. But I'm going to say that my answer that I'm going to try to make a pitch for in this talk is that a good objective for nonlinear function approximation is this thing I'm going to call the generalized projected Bellman error. I'm giving a name to something that sort of already exists in the literature. And specifically that when we're picking this objective, when we want it to be the right objective, we're going to have to pay attention to the choice of weighting we have in that objective. And that choice of weighting might actually be different than the actual true ideal weighting we care about in our value error. So let me tell you more about both of these things. Okay, so the outline of my talk, I'm going to mainly try to get across these three things. First, I'm going to show you what is this generalized projective Bellman error that lets us go from the linear case to the more general setting. Then I'll talk about why should we care about this state weighting? Like, why is that something that's worth a high priority of our time? And the last thing is, now that we have this objective, we still want to ask, how is it going to be practical to use in practice? And there's at least two ways that we could try to optimize this objective. And I think one of those ways is going to be a much more promising direction that makes it more likely that this objective will actually be adopted in practice. Okay, and then if there's time, then I'll actually show you some positive empirical results. This paper is not yet published, but it's sort of an extension of an ICML paper from this year, and I have a working paper up on my website if you'd like to go check it out. And otherwise, I also have the slides for this talk on my website. Okay, good. Let's start with the first thing. Let's start by deriving this generalized projective Bellman error. Okay, so to derive this, we're really just going to rely on this beautiful result from Bo Dai and others from a paper called Learning from Conditional Embedding, this title here. And so really this does most of the heavy lifting for us. And we're just going to take these ideas and just do the sort of natural small next step and define a few things that's going to help us make some traction on this problem. So if you haven't read this paper, you should go look at this paper and follow up papers from Li Hong about speed and about the kernel Bellman error. And now also Nan Jiang just posted a cool paper earlier that's related as well. So the really nice insight from this work is that we can take the Bellman error and we can reformulate it as a saddle point problem. So it's going to have this min-max form where we have an inner maximization over this auxiliary variable h, and that h variable is estimating some part of the objective. Okay, now with that form, h is giving us an estimate, but we want to get as close as possible to the true Bellman error. So there's these nice results that show that we can use different estimation approaches for h, for example, non-parametric approaches, and get a really close estimate to the Bellman error. Okay, so the key insight for us here is that this line of work is actually getting us now practical algorithms to nearly optimize the Bellman error, where we can get a really close approximation to the Bellman error, but there is still going to be some approximation. So it sort of reopens up the avenue to nonlinear value estimation, because now we can start looking at the Bellman error, which more naturally applies to the nonlinear setting. So that's sort of the direction I was going there, is how can we do as good of a job estimating the Bellman error as possible and optimizing that? And I'm gonna go just a slightly different direction and ask, how can we use this to derive a generalization to the linear projected Bellman error? So that's what we're gonna do. So we're gonna build on this work and go in that direction. Mostly I'm gonna take what was already in that work and just formalize it in the language of projection so that we can more easily talk about some of the algorithmic strategies used for the linear projected Bellman error. Okay, we're going to talk about the finite state case. Here's some notation we're going to use. So I'm going to assume we have a parameterized value function b hat with parameters w. Here's the standard TD error, and just note that when I talk about expected value of the TD error parameterized by the weights under policy pi, that's exactly reflecting what this Bellman residual is. So it's just this Bellman operator here, but I'm going to be often writing it in this form instead because it's going to be useful for manipulation. Okay, great. This is actually sort of an educational talk, so I wish you could interrupt me as we go along, but maybe if someone really has a burning question or clarification, I actually can pay attention to chat as we go and I might be able to respond. Okay, so the steps for this are actually very simple, which is one of the things I love about it. So first, let's just write out what the Bellman error is. This first line is just the definition of the Bellman error. We're looking at for across all states weighted according to D. So this outer sum is an expectation over states. We're just asking what's my expected Bellman error from that state according to policy pi. Now the first step, we're just going to rewrite this using this conjugate form here. So when we look at a squared function, the conjugate form looks exactly like this, where we can rewrite it with the max over a different variable h. And here now our y just corresponds to this term. That's the thing that's being squared. So that's what you see exactly here. This is our y, we just have an h, we're maximizing over h. Okay, so first step is apply the conjugate form. And then the next step is that we can bring this max outside of the sum, as long as our h can represent the same h's that we would need it to represent. So here we have a finite state case. As long as we have the space of all functions, then our h of s, we can always set it to be equal to what we needed it to be in this inner term, so we can pull it out. And in fact, we know exactly what this optimal h is for this maximization. H of s here is trying to approximate this expected TD error. So if we use that h, then that's exactly the h that would be picked for this inner term. Okay, that's it. That's the reformulation. And now you might ask, why is this a useful thing? Well, the useful thing now is that we have two variables, but this auxiliary variable makes it really easy to compute the gradient for W. So if I give you an estimate H, then now the objective, this inner term here, I have two variables, a W and an H, that's being stacked. We have this min-max form, and the computing the gradient of this term, H is some constant, and you just compute the gradient here with respect to W, and that's straightforward. It's exactly this term. So we can now get a stochastic sample of our gradient by computing the gradient of the delta, and H of S is representing this expected value of delta out in front. And now we can just learn these two things together, or H, for example, it might not even need learning. You might just estimate it using some non-parametric approach. Okay, so that's why it's useful. Now you might say, okay, then aren't we done? We now can optimize the Bellman error. Straightforward, I'm going to go apply it to my neural network. I just need to estimate this extra H somehow. But the first point is that I already mentioned that there is one other problem, which is that the Bellman error is non-identifiable. And so we're going to go a little bit further. We're going to talk a little bit about what should we pick for H. That's going to help us resolve this question about non-identifiability, and then move to this generalized projected Bellman error. Okay, so this is going to feel a little bit like an aside but one thing is that I think it's kind of fun to talk about this non-identifiability problem, but it also naturally sets up to the projection. Okay, so the first thing we can do is we can notice that we can actually get a natural identifiable Bellman error by using this conjugate form. You may not know about this problem with the Bellman error. There's this nice example from the Sutton and Bartow book that I've referenced here that simply shows that if you had this partially observable setting, so if you have a data stream where the agent might be, say, in one of these two MDPs, but it has no idea. It just sees that it always gets this observation bit that's equal to 1. So the data stream between these two MDPs for the agent is going to look exactly the same. So we couldn't hope that it's going to learn a different solution on those two things because the data stream looks exactly the same. But the true solution to the mean square projective Bellman error for these two settings is different. Okay, so that's what the counter example shows. And really the issue here is that the Bellman error is defined on quantities that are not available in the data. And so what we can see is that sort of it's a way to talk about in the conjugate form is that the H is defined on quantities that are not available in the data, but the H is now a variable that of course we are trying to estimate. So it makes no sense to define H on quantities that are not available in the data because I hope that's just intuitive. So the natural thing to actually have defined our Bellman error as is for this H to be defined only as the set of functions on the space that is actually given to the agent. So we're still going to allow H to be any function it wants. It can be a crazy function, it can be a non-parametric function, but it's only allowed to take as inputs the actual information that's in the data. And then now we're going to remove this identifiability problem. Well, because that's sort of one neat thing that the conjugate form gives us. And the other, but then it's also sort of starting to highlight, well, then, maybe we don't just want to restrict H this way. What happens if we continue to restrict H? And that's going to bring us to our generalized Bellman error. So more generally, as we start restricting the function space for H, we're going to get a projection on the Bellman error, and that's going to give us our generalized projected Bellman error. So just to explain some of the notation on this slide, here I'm just writing what this projection means. So this is saying that this is the projection of some vector u onto the space H, the function space H here, with weighting D. So it's saying go find the H that's the closest to you in my space H, weighted proportionally to D. Okay, that's what this projection operator does. So if we take this, what I'm going to now just immediately define as the generalized projected Bellman error, we're just saying I picked some space H. This H no longer has to be H all. That's the all was dropped from here. Could be more restricted. Then we're going to do multiple steps and find that this gets rewritten exactly as this projection of our Bellman error. Okay, and so this is I'm calling this a generalized projected Bellman error because, by picking different choices of H, you sort of get some of these natural settings that we're used to. So if I pick H here equal to the same space as the value function space, and it's equal to a linear function space, so they're both a linear function space, then this actually gives us exactly the linear projected Bellman error. If otherwise, though, we can actually generalize them both to a nonlinear function space, and then that gives us what is a natural extension of the linear projected Bellman error to the nonlinear setting. We've already seen that if we restrict H to H all, then we're going to get an identifiable Bellman error. So we can kind of think of this identifiable Bellman error also as a projected Bellman error. And then more generally, we could have this whole space of possible projected Bellman errors if we pick an H that's a larger function space than the space for our value function. Okay. It seems like there's a fun discussion going on in the chat, but I'm gonna have to keep going. Okay, so that was the first thing I want to tell you is here's a natural way that we can generalize to get a generalized projected Bellman error just by using these beautiful insights about how we're going to approximate the Bellman error. Okay, next point. So given that we have that objective, now we can ask one more important question. So I should say here, I've kind of highlighted the importance of this choice. How should we restrict H? And then of course, another thing here that I haven't mentioned is D. So I think D is sort of something that's often overlooked for value estimation, especially in prediction. In control, the weighting is much more focused on. But in value estimation, we might want to ask a little more about this. So to sort of understand what should we pick for D, what we really want to do is turn to some of these nice value error bounds that exist in the literature that can give us some insights about what is the role of D in getting good bounds on the value error. So let me explain this result here. This is just saying that if I get my value function from my generalized projected Bellman error, so this is not about any kind of approximation, just saying if I got the actual true solution for my generalized projected Bellman error, that true fixed point, and I want to know how far is it from the true value, b pi, then this can be upper bounded by this worst case approximation error. So this term here is just, this is saying get the closest point in my function space f. That's the best I could have hoped to do by projecting b pi. So this is my approximation error, and then I'm going to add some constant out in front here. Okay, and so for this constant, this is just telling us what the norm is of our projection. I'm not going to focus on that right now. But the key thing is that we would, of course, like this constant to be small, and particularly we would like it to be bounded. But actually, if we're not careful about our choice of D, this side can actually get, this norm here can actually get very bad. So let me give you an example. So there's this really beautiful counterexample from Zico Coulter, where it just takes a very simple two-state MDP. It has very small approximation error. So the value function space that you have can actually very nearly approximate the true v pi. And what he shows that if you take a D that corresponds to the off-policy stationary distribution, so equal to, let's call it dB, then the solution from the projected Bellman error can have arbitrarily bad value error. So even though you're weighting the value error by dB, you go and compute the optimal projected Bellman error solution, also weighted by dB, you can make that number shoot off. You can make the value error get worse and worse and worse by making some choices in your behavior. It's a pretty cool counterexample. So what this is telling us is that just saying, it's probably okay if I just use the stationary distribution for the behavior policy. Well, the answer is it might not be okay. It might actually be really, really bad. But one thing we can do is, so there's this work on emphatic weightings. Li Hong mentioned them, where we can actually make some guarantees that we will have these nice bounded constants here, and we will have upper bound on the value error for our mean-squared projected Bellman error solution if we use a different weighting. Okay, so this first result is saying if I change my weighting D from dB to this other thing called an emphatic weighting, then I will actually get this nice result that says I have some upper bound on my value error that's just proportional to the approximation error times some constant, and this constant's sort of reasonable. And then we can say something even more interesting, I think, which is, it's sort of cheating that we get to pick our weighting and our objective, and we get to pick our weighting in our evaluation. What if I just picked all weight on one state, and then I can easily satisfy this? So we can additionally say if I gave you agnostically some other weighting, let's say I gave you here this stationary distribution weighting that kind of covers the space reasonably, even under that weighting, even though I optimize my objective according to this emphatic weighting, I still get this nice upper bound on this value error. Again, there's only so much we know actually about what these constants look like. But we've also been running a few experiments to see if some of this stuff happens in practice as well. And I'm really running out of time. So I'm going to quickly just summarize what this slide is saying. So what all this is saying is we ran with the projected Bellman error and Bellman error across many different problems with different feature spaces. And the key conclusion here is that when we optimize our objective with the stationary distribution weighting, this dark color is bad. And so the error is bad in general, even when we use the weighting dB and the true value error, which is what this is showing on this side. And when we change the weighting in our objective, it significantly improves the quality of our solution. This is not about optimization online or anything. It's really just about where do you converge to. So even if you had the best algorithm, it really optimizes your objective well. If you're not careful about weighting, you're going to converge to a poor solution. Okay, the last thing I'll do, and I think I can summarize this quickly in 1 minute. So we sort of have what I think is a reasonable choice for the objective for nonlinear value estimation. And then to make it practical, I think there's one other important point, which is when we're sampling this gradient for this objective, we want to make sure we are not too reliant on how accurate our estimate H is. Okay, so let me, there's sort of two different types of strategies that people typically use for the linear projected Bellman error to get a sample of the gradient. One is this saddle point update, and the other is this gradient correction update. So if you're sort of used to this literature, the first one corresponds to GTD2 and the second corresponds to TDC. And this one is just a gradient I showed you earlier. It's taking our estimate H and it's computing this gradient of the TD error. One thing you'll notice about this update is that it relies heavily on H. So imagine you start H near 0, or like, it's randomly initialized near 0. The early updates to W are going to be pretty poor because it's being modulated fully by this H. The gradient correction update instead moves a few terms around and gets an update that looks like this, where the first part always includes a true unbiased sample, so it has this TD error term here, and then you only use the H in what is this gradient correction term. So it relies a lot less on the estimate for H. Okay, there's some nice reason to think that's a good idea, and experiments suggest it's a good idea. There's some more difficulty in analyzing the gradient correction update because it's not really a true gradient update anymore. But we have just found consistently that this is the right direction to go. And there's nicely some of the analysis of how to derive the gradient correction update actually extends to the nonlinear case as well. We go through this in the working paper. And it suggests a natural way to try to estimate this H in the nonlinear setting. So that's what we used in the ICML paper. The very simple idea is just to take QLearning. Let's say we did prediction and control, but I'll just tell you the control one. You can just take something like QLearning and add gradient corrections, where you would do your usual thing. You have this green part of the network, that's your usual QLearning agent. All you do is add an extra head to the network that's going to estimate H. None of these gradients flow back, which is what's suggested by the analysis. It actually just suggests it's better to put this extra head on the network. And then these action values are updated with the gradient correction form. Okay, and sort of the exciting result that we found was that gradient methods actually seem to help. So both QC and QRC, the R just means regularized corrections, but they're both using this network structure I just showed you here. They actually both outperform QLearning, and in some cases by quite a lot. So for us, this was really amazing and surprising, because one thing we often find when we run experiments is that QLearning and TD perform pretty well, and it's pretty hard to outperform them actually. So this was an exciting result for us that gradient methods were actually helping. Okay, so let me just conclude then with a summary. So really, these are the main points that I wanted to get across today. One is that the generalized projected Bellman error is a natural extension of the linear projected Bellman error to the nonlinear setting. There's this additional nice benefit that this projected Bellman error helps resolve questions about the Bellman error, both about identifiability and how it's connected to the linear projected Bellman error. And whenever you're running these algorithms, the role of the weighting shouldn't be overlooked, because you might actually find it impacts your performance a lot. All right, thank you very much.
Okay, thanks a lot. This is really interesting talk. So we have a few minutes for questions. I open the floor for questions now. I see that we have
I'm just going to start going through chat. I see Amir Masood's question about how is the generalized projected Bellman error different from the nested optimization given by Chaba Mohammed Shah you had a few years ago. Yeah, actually, I'm going to agree with Nanjiang. I would love to see that formulation. I know there's a lot of work in this area, so maybe there's also the Antosh paper. I could tell you how it's a little bit related to that. It is definitely related to several papers, and I'd love to tell you more. So one thing I do want to emphasize here is that a lot of what I've talked about today is sort of summarizing a larger body of work that is exploring these questions. And by going to the working paper, it more emphasizes how this is relying on a lot of important results in these other papers, and you can go find those results in those other papers.
So, Martha, great talk. I have a question about the weight correction thing. I think I understand its role in the policy evaluation, in the evaluation setting. But for the optimization and control setting, what's the, I mean, I may have like missed that part. Is the recommendation still to like correct to the distribution that would be induced by your current policy, or what?
Yeah, great question. Yeah, so you mean up here, I've made the comment that the emphatic weighting makes the fixed point for the mean square projected Bellman are better for the value setting. And for the control setting, I still have no idea. So the control setting for me is newer. I'm not even sure exactly how you define the emphatic weighting because your policy is changing all the time. Like you said, you could define it to be the current policy's emphatic weighting. But I don't know what that means for the Bellman optimality form.
Yeah, so actually we have some work like in the earlier paper we sent out, we have some like, there's some pretty simple analysis that you can show that in the control setting, what matters, the distribution induced by your current policy matters, but still the distribution of the optimal policy also matters. It's like these two things like together, or whatever policy you want to compete with. It's like the Bellman error under both these distributions give you a tight control over the suboptimality of your policy. So that's what I feel like in the control setting, you may not want to like directly just completely like reweight to the on-policy distribution of your current policy.
Right, right. It is true that the control setting is a little different because here, at least when we're talking about the value estimation setting, then we sort of have two similar-ish things on both sides of the equation. Like we are trying to estimate some values V, but in the control setting, you're saying how good is my policy? But then you're looking at like Bellman errors, which are more different. But anyway, I was actually reading your paper right before this talk since you mentioned it, and it looks like it's full of lots of really nice results that maybe we could try to incorporate into the working paper. Because one of my goals actually for the working paper is to go and summarize all these different ways people have tried to bound these errors and see what we can do to extend for this particular thing.
Martha, we have a question from the attendees. Could you see that question?
Okay, let me pull up you mean like there's a Q&A?
Q&A.
Okay, let me just, I always have to get, 1 second.
The last one about projection operator.
I have this, okay, there we go. I have this thing where I hover over the top panel and it takes forever to show up. Okay, okay, good, Gary Gay's agreeing with me. I felt like I was the only one who had this problem. Is the projection operator contraction for the nonlinear setting? And if yes, what are the assumptions in if it's a contraction? Okay, good question. So whenever we write down the projection, oh, okay, maybe what you mean is like the projected Bellman operator a contraction for the nonlinear setting. Like whenever we talk about doing like Bellman fixed point iterations, we're sort of imagining we're doing this iteration with the Bellman operator and the mean square projected Bellman error case. We sort of analyze what's the properties of the projected Bellman operator. Maybe that's what the question is there. Actually, when we talk about this projection, then it still actually applies for the nonlinear setting. Like you can characterize the projected Bellman operator for the nonlinear setting in the sense that our function space can be a general function space. So then in that case, the projected Bellman operator can be a contraction. And in some cases, we know that it is not a contraction. Say, for example, some cases in the off policy setting. If that answers that question.
Yeah, well, I suppose that the question should be whether this is this projection operator that we have is a non-expansion or not, right? So
right.
Can it happen that it is going to like throw further away the arguments than they were before? And I guess the answer for that is as long as your function class is convex, which means that it includes all the convex combinations of the functions, then I think this should hold.
Right, right, exactly. It's not a linear versus a non-linear thing.
I have a question about some time. You use two different function space, and my question is it related to the oblique projection point of view of learning value function, if you know it? If you see what the oblique projection point of view is, basically is what you want to do is really to project the value function, but you don't have the value function, so you can do the project. You can minimize the residual. You can do LSTD, which is a projection, and then you minimize the distance between the function of the projection. And if you change if you take a second hypothesis space and you change, you do an oblique projection, which is orthogonal according to the second hypothesis space, you can recover the true value function, but it's circular in the sense that finding this hypothesis space is as hard as finding the value function. So is it related to this kind of approach?
I didn't hear all of that, but I'm going to start off by saying definitely that this, for example, this projection operator and this result is simply writing some of the results for this case that Scherer has and that like Janie Yu and Bertzakis have about oblique projections. Because here this is exactly oblique projection. This H is this non-diagonal matrix. Okay, and then I think you said when it comes to choosing that space, there's some circular thing going on, but you cut out, so I didn't exactly hear what you said there.
Yes, that's what I was saying. We can say what the optimal space for the oblique projection is, but knowing this optimal space roughly requires knowing the value function, which is what you try to estimate. So the question is how to choose this space.
Right, I agree. Okay, now I understand. That comes back to the how do we choose that H set? And I honestly don't have a great answer for you. I'm not sure yet what we should choose. I'm going to hypothesize that like Li Hong and Bo and others have said we should try to make that projection, that space H as big as possible. We want to project as little as possible. I may be putting words in their mouth. Whereas my proposal is that H space should actually be parameterized using the gradient of the value function for the state, because that seems to give us this nice algorithm that performs well in practice with this gradient correction update, even though I know that means we're restricting our space H more. What I would really like to do is see if we can say something more general about it from the theory, but that I don't know yet how to do.
Thanks.
Okay, maybe we have time for one more quick question before we move on to the discussion session. So maybe I can take the opportunity to ask the question I always have about the example in that Martha you mentioned early in the talk, that there is an example, a simple example where, yeah, exactly, this non-identifiable Bellman error. Do you think this is a very serious issue of using Bellman error as a objective function? This is quite common in other learning problems, is supervised learning, right? We don't expect identifiability, but it seems things work pretty well there. Could you elaborate a little bit more on that?
Actually, for me, the conclusion from this is the people who are optimizing the Bellman error are doing the right thing. And also, this example is also sort of right. And in some sense, we're all trying to just do the slight modification, which is the identifiable Bellman error. So in some sense, this is like a win for everyone. We were all right. That's kind of how I feel about this answer. But anyway, I guess, is it a serious problem? I think in most cases, we maybe aren't actually going to see this problem. Like when we are trying to approximate the Bellman error online with all the strategies that are currently being used, I think implicitly they are optimizing the identifiable Bellman error is what's going to happen. So I don't know, I'm not sure if that really answers your question, actually.
Yeah, it's sort of, and this question may be, it may be more appropriate to discuss later on, perhaps in the discussion session, and since we're running out of time, so maybe it's time to move on to discussion, and thank Martha again for the talk, and without further ado, I'll let Gertrude take control of the discussion. Thanks.
All right, that's wonderful. Thank you, Li Hong, and thank you, Mark, for inviting me to host this, and thanks for the wonderful talks so far today, this afternoon, I would say, for me.